So let's just take f then. So since we have f belonging to w11 omega, we do need it to be continuous. This is, in this case, important. And then if we have z belonging to omega, then we have that f of z is equal to, so I should specify that omega is contained within complex numbers, and we're mapping into the complex numbers, okay? Okay, so then if z belongs to this point, then the first part is just the standard part. We actually want it to be in the closure for it to be defined on the boundary, is this thing. Boundary of omega. Today I can't write. Let's do that again. Boundary of omega, f of zeta, zeta minus z d zeta. And then the next part is this part we get from the anti-conformal part of the gradient. So it is f by d zeta bar d zeta, and then zeta minus z d zeta. But we have to be a bit careful because we can't have this defined in the standard sense, because as I'm about to show you, the kernel doesn't blow up, this kernel, which means this thing underneath doesn't vanish. So this thing has to be minus the limit as epsilon tends to 0 of this thing. This is d zeta of, maybe I write a double integral just to emphasize that this is over this, okay? So this is what we got from last time, so that's where I cut off the video last time, and this makes perfect sense, right? So this limit does indeed exist by the arguments that we had, and this is a true fact, okay? So that's, if you look back at the video, that's where we stop. That's just applying this divergence theorem expressed in complex coordinates. It just comes down to applying it to this function. Tau goes to theta of, well, in this case, I call it, I'm using zeta now. So zeta minus z of zeta. So just in the divergence formula, complex divergence theorem. Okay, that's what we did. And we're going to use this to define an operator called the Cauchy transform on mappings. It's sort of it's hopefully motivation for why the operator first exists. The operator makes sense. What we know, so given some f, which is compactly supported C infinity from here to here, yeah, then for sure it's in every possible nice space. Yeah, it's in every possible nice space. And then take z inside the complex plane, and then let's apply our formula. So we have f of z equals 1 over 2 pi I integral around the boundary of the ball of, we don't have to center it around anything, so let's just do it around 0. Why not? And then we have f of zeta over zeta minus z d zeta, okay? And then minus 1 over pi like this, double integral around the boundary of the ball, radius 0, and then the df by d zeta bar, d zeta, zeta minus z d zeta, okay? Cool. Now, since we have compact support, as we let the r tend to infinity, then this part will just vanish, right? We'll ultimately be outside the support of f, yeah? Yeah? And since we are in C infinity, we have all the integrability we want, this thing now we understand not in the sense of principal value, but in the sense of a natural integral. This thing does converge. Yeah. So no limit here. Yeah. So there's only one limit in play when we take r to infinity, and that's the limit as r goes to infinity, right? So letting r to go to infinity. So this is true for all r, which is actually bigger than z, because we want z inside this ball for this to make sense, right? So take the limit. Tends to infinity. Then we have this, that f of z is equal to minus 1 over pi double integral. And now inside the entire complex plane, we don't, any sequence going to infinity will satisfy this. So this is indeed meaningful as the integral over the entire complex plane, like this. D zeta. Yeah? Everybody with me? Yeah? So for functions, let's say w belonging to C0, C infinity, complex numbers to complex numbers, we can define the Cauchy transform. C of w by this thing. Actually, I'm going to write down also the variable. So we're going to C of w. This is a function, so acting on variable z, it's given by this double integral minus 1 over pi, like this, over the entire complex numbers, and then we're going to just put w over zeta, w of zeta, zeta minus z d zeta. Okay, that's how we're going to define it. This is a linear transformation. Yeah, it is well defined by the discussion we just had before, that around the singularity zeta we don't have an issue with having to take a specific limit. This limit, the integral of this thing around the ball of radius epsilon around z will vanish as epsilon goes down to 0, right? So we have no problems with the singularity here. And this thing is just well defined as we take r going into infinity. Well, this thing is just this is the integral of larger and larger domains as r going to infinity, but it's well defined because this thing has got compact support, right? So we don't have a problem. So this integral is indeed finite. It does make sense. It's a reasonable integral, and this is a linear operator, yeah? And what our calculation above says that if we take f, which is the infinity compact support, and we take the Cauchy transform of the anti-symmetric part of the derivative, yeah, then this thing, put it in this formula, we get exactly this thing, and it turns out it gives us the function back itself. Okay, that's what the calculation above just says. Yeah. Yeah. So we take a smooth function, we take its anti-conformal part of gradient, then the Cauchy transform strangely inverts that. Yeah. That's what it does. Cool. Now we're going to show that this relation is commutative, so that if we take the anti-symmetric part of gradient of the Cauchy transform of some function, that will also give us back the function. So that will show that the Cauchy transform exactly is the inverse of taking the symmetric part of the gradient. That's our goal. Okay, that's what we're going to, at least for C infinity functions. Don't be freaked out by the fact here we have f of zeta bar and f of z bar. All this means is that we've taken the anti-symmetric part of the gradient, right? And I write zeta bar because the variable is zeta here, right? Maybe better notational would be just to put f bar or something like this, yeah? Yeah. So here we've taken the anti-symmetric part of the gradient, and then that's what we have inside here, yeah? Everybody happy with that part? Yeah? Cool. So let's consider another operator. So consider this operator, L of f, which is defined to be the double integral over the complex plane of f of zeta log of z minus zeta, like this, d zeta, okay? Again, we're defining it for functions belonging to compact support, complex plane, C infinity. And again, this thing does make sense. This logarithmic singularity is blowing up incredibly slowly at z, right? So it's easy to see that this is actually integrable. It's got a finite integral, yeah? Cool. So this thing is a nice well-defined operator. So well-defined. And what is cool about this thing is that it works well with translations. So let's actually write down that. So this acting on z is equal to this. Okay. So let h be some complex number, and then define f of h of z just to be what happens when we shift forward by this, so h of z plus h. Yeah. Then let's see what happens when we do L of f of h, like this, acting on z, like this. Let's see what happens. And then this is the double integral of the complex numbers, f of, so let's write in what it is. So it's zeta plus h, and then log of z minus zeta, like this. Right. This is what we have, yeah? And then let's shift things around. Let's define zeta tilde to be equal to zeta plus h. So in particular, we have that zeta is equal to zeta tilde minus h, right? Let's make that change of variables. Since we're integrating over the entire complex plane, we still have the entire complex plane. So we have f of zeta tilde, and then log of mod z, but now we're minusing z, which is this. So it's going to be minus z, so it's minus zeta plus h, or minus zeta tilde plus h, like this. The zeta tilde, right? But then this is exactly the same as doing the logarithmic, I don't know what this is called, but I'm going to call it logarithmic transform. The logarithmic transform of f, but now we are doing it, and then we're looking at what it is at z plus h. Yeah? Yeah, because this thing is exactly evaluating the logarithmic transform of f at z plus h. Yeah? Cool. So that means that these guys work well with translations, which isn't true with the other transform, the Cauchy transform that we talked about, but it's going to be a useful property for us. So define d of h of f of z to be equal to f of z plus h minus f of z. Okay, this is not dividing by h. This is just taking this difference, right? We're not going to divide by h yet. No? Then, if we do L of d of h of f like this, then what's going to happen? We are just going to get, this is the same as d of h acting on L of f, like this, just by linearity. Yeah. So this part will be this first part here, right? And then this minus f. Are you happy with that? Yeah? Yeah? Cool. And that's going to allow us to actually take derivatives through this expression. And I say through this expression with some caution because it means passing through the limit, which we'll have to think about because we can't pass the limit through an integral without the right stuff happening. But we will have the right stuff happening because we have a function f which is c infinity, so the partial quotients will converge uniformly to actually the actual derivatives. And then this thing is nicely integrable, so it's actually going to be fine to take these partial quotients through the integral and have the derivatives commute. But let us get to that shortly on the next board. So what have we learned? We've learned that if we take the logarithmic transform of this guy, let's write it like this, that's the same as doing this. Okay, and let's recall what the logarithmic transform is. So logarithmic transform of f is this double integral. This thing is indeed just f of zeta log of zeta minus z d zeta, like this. Right? So let's look at that thing. So then when we do L of this thing, of f of zeta, then it is this thing 2 over pi double integral of f of zeta plus h minus f of zeta, no, over h, just like this, times the log of zeta minus z, like this, d zeta. But then we can put this difference operator onto the log instead of onto the f, if we want to. Right? We can change variables and put this onto the log instead of onto the f. Right? So then this is, if we write this out separately, so the entire complex plane, then we'll have d zeta minus 2 over pi d zeta, just like this. And now we can do this change of variables. We can let zeta tilde be zeta plus h, like this, and therefore zeta equals zeta minus h, right? And then this thing, all right, is pi. This thing, f of zeta tilde, and then log of absolute value of zeta minus z minus h, like this. D zeta, right? And then minus this other thing here, minus this thing. And what's that saying? That's saying that we have this. F. Now I'm going to change the variable back to zeta, and now I'm going to write dh of log of absolute value of zeta minus z, like this, where the dh is respect to the variable z. Okay. D zeta. So we're going to be able to pass this partial quotient now onto this log of this thing, which will allow us to differentiate it, which is going to be a useful thing for us. But to do this calculation, we have to differentiate a little bit inside this thing. So what we're actually going to do is we are going to take the partial quotient. We're going to take the partial difference in order to extract the symmetric part of the gradient, right? And therefore, what we're going to be doing is taking the derivative of this guy with respect to the symmetric part of the gradient, and it's going to turn out that that's going to give us exactly the Cauchy kernel. Okay, that's the calculation we're about to do. So let's look at that a little bit carefully. So what do we do if we take this thing? If we take the symmetric part if we take the anti-conformal part of this thing, like this, then what is this? This is equal to 1 over 2. Is it plus or minus? I think it's plus, right? d by dx plus I d by dy of the log of this thing, zeta minus z, like this. Let me make sure got that right. We're not going to do the z bar, we're going to do the z part. So we're going to do the z, and then it's a minus. Like this, yeah? And then let's see what happens if we take the partial with respect to x of log of the absolute value of zeta minus z, okay? Then it's going to be, so it's just a chain rule, so it's going to be 1 over zeta minus z, and then we're taking the partial with respect to x of the absolute value of zeta minus z, like this, yeah? Which is 1 over zeta minus z, and then the partial with respect to x of, let's write out in coordinates what this is. So I'm going to write z is equal to x plus iy, like this, and then we're going to have zeta 1 minus x squared plus zeta 2 minus y squared 1 over 2, like this, yeah? And let's just do this calculation, and we have this, and we're going to have a half from this, and then differentiating it. So we're going to lose this thing. I'm going to differentiate this factor, so we're going to get just zeta 1 minus x, like this, yeah? And if we do d by dy of log of zeta minus z, then the same stuff happens. We're just going to get zeta 2 minus y over zeta minus z, right? So then when we do the dz of this thing, So we need a minus sign from here. And then we need a minus sign from here. Like this. And yeah, okay. Okay. All right, so if we do this, whoops, d by dz of this entire expression, log of zeta minus z, so value like this, then we are going to have just a half of this guy, so a half, and I'm going to write this as x minus zeta 1 like this over zeta minus z, and then we're going to have minus I, and then this thing I'm going to write it as y minus zeta 2 over, I'd rather write z minus zeta. It's going to be symmetric, but let's just write it like this. Yeah, it's going to be like this. Happy with that? Yeah. And then what's that? That is the same as a half times the complex conjugate of x minus zeta 1 plus I times y minus zeta 2 complex conjugate over zeta minus z or z minus zeta. Yeah? But this thing on the top here is just z minus zeta. So this is a half of z minus zeta over complex conjugate over z minus zeta, like this. Yeah. Cool. So that when we get to this thing, then this expression right here means that we can't exactly take the partials that we want, right? We can take the partials to recover the real and the complex part. So to recover this partial d by dx and this partial d by dy. Yeah? We have the right to do that. So that when we do that, we can actually pass through the limit because of smoothness of this thing, and that allows us to do the following. We can simply take the derivative, the conformal part of the vertical derivative in here, and then have it act on this thing, right? So let's run off the entire expression. So in here, we can have L of the conformal vertical derivative of f at z. If we can pass through the integral, which I'll talk a bit about in a second, then it's going to be the same as the double integral of the complex numbers of f of zeta. And now we're taking the conformal vertical derivative of this guy, which we've calculated to be just this guy, right? And then this thing we can simplify a bit, therefore, because what is this? This is 1 over 2 of zeta minus, or z minus zeta bar and then z minus zeta bar times z minus zeta bar, right? And then one of the z minus zeta bars cancel, and we just have 1 over 2 of 1 over z minus zeta. Yeah. So let's put a line differentiating all these things here. Yeah. So when we are at this stage, then we have actually this is just a half of 1 over z minus zeta, like this, d zeta, yeah? And then the halves cancel, and then I prefer to write it as zeta minus z and then have a minus sign, so then this is exactly minus pi, double integral over the complex numbers of df by d zeta minus z, d zeta, and then this is exactly the Cauchy transform. Cauchy transform of f, like this. Yeah, cool. So we have this cool identity. We are going to use this in the next class to prove what I claimed, that ultimately, that this Cauchy transform is the inverse of the z bar operator. So we'll use to show that Cauchy transform composed with the z bar operator is the same as the z bar operator composed with the Cauchy transform, and it just gives the identity. We have this is z bar, We have this part, which was the part which just fell out from this identity from yesterday, which is just the divergence theorem in complex coordinates. This part is the part we're aiming for, and we're going to use this stuff here to allow us to conclude that. That's our mission. And it's a little exercise for you if you want to give that a go, to just try and use this to conclude this. And the hint is that when we have something smooth, then partial derivatives or derivatives commute. Right? And so prove the similar, this identity shows us that we can pass partials through like this. In this thing, we put the derivative on log because it was convenient for us, but use that thing and use the fact derivatives commute and this identity to see if we can do this part as a little exercise. And that's what we'll actually do next time. Have a great day.